Well, thank you for that kind introduction. It's a real pleasure to be talking here today. Today's talk I've called Where Angels Fear to Tread, and I'm going to be talking about the use and misuse of graphical models. And there's a couple of pictures on the front here. The middle panel, some of you may recognise as the cover of the very excellent textbook from Daphne Collar and Nia Friedman about graphical models, which I highly recommend, by the way. And over on the right, there's a picture of a cover from another book, which perhaps many of you won't have read. It's by E.M. Foster. It was written over 100 years ago, and it's called Where Angels Fear to Tread. And so today, the theme of this talk is the potential of these models, but also how their pitfalls associated with them and how they may be avoided by just being sensible and careful, I suppose. So anyway, to jump right in, I'm just figuring out how to change my slide, but there we go. I thought in talking about graphical models, I'd jump right into a real example. This was work that that we did for the Paul Ramsey Foundation, and there they were looking at causal inference for childhood obesity. As we all know, childhood obesity levels have been increasing enormously. And the million-dollar question is, you know, what's the causal pathway? If we knew it, how could we possibly intervene? And this is joint work with some people from Sydney University, Andy from the Maths and Stats, Roman from Computer Science, Richard Morris from psychology, Steve Simpson is a world-famous nutritionist, and Louise Bowers, probably one of Australia's foremost professors of childhood obesity. So it's a very eclectic group of people who did this work, and as you'll see, one of the other themes that's coming through is that you know, data science alone is never going to answer these very tricky questions, and we need to be able to work with lots of other people. So how can we possibly intervene? What is the causal pathway as opposed to just knowing that things are related? So we have a whole bunch of data. I'm not going to go too much into it other than to say it's a wonderful data set. It's been collected since 2003. And what happens is there's two cohorts, and every 2 years, several questions are asked of children and their parents, and their responses are incorporated into this LSAC data set. And that's the data that we're going to be using. The real quantity of interest that we're interested in understanding is the child's body mass index, and we have many variables on the child's family, what happened at school, and there's a whole range of data types, discrete and continuous. There's many more than 1,000 variables per child, a very rich data set. And so, you know, we were hopeful when we did this that we would uncover some very important links about childhood obesity, which could be acted upon. And I think that's also key, trying to figure out what you actually can act upon. So to take you through some of the problems and how graphical models work in causal inference, I'd like to take you through a very simple example. So I'm going to select 3 variables. We've got socioeconomic status, the mother's education, and the child's BMI. Now, the child's BMI is in purple, and the reason for that is I'm going to treat it differently from the other variables in the data set. I'm going to say a priori that it can never be causal. So that may be a wrong assumption, but it's an assumption that I'm going to make up front, so that it cannot be a parent, the terminology is, to another variable. It's always going to be what's known as a child. So it's an end node of the graph. And in order to infer causality, what we're actually going to do is constrain ourselves to look at a subclass of graphs that are called directed acyclical graphs. Now, the point of directed acyclical graphs is that instead of just relationships between variables, you've got the direction of the relationship, and hence the term causal. So that's the directed part. We know that not just X and Y are related, or not that just mother's education and socioeconomic group are related, but we can say that one causes the other. That's a directed graph. The acyclical part is that we can't have X going to Y, going to Z, and then going back to X again, so forming a cycle. That's not allowed, because then that would also mean that we can't infer causality. So we're going to limit ourselves to that class of graphs, and a DAG works by, that's a directed acyclical graph, by finding what's called conditional independent relationships amongst the variables in the network, and we're going to talk about that over the next slide. So that's effectively, this is setting up a really simple problem that you might want to use a DAG to answer. Now, here I've listed some possible DAGs and the way they may appear to you. As I said before, the child's body mass index always is appearing as an end node, not as anything that is causal. And so some possible graphs, I've listed them here. The first two have both socioeconomics and maternal education independent of each other, but both leading into a child's body mass index. The second one has the causal relationship that socioeconomic group leads to maternal education, leads to body mass index. The next one just reverses that causal relationship to start with maternal education, then socioeconomic group, and then the child body mass index. And the last one has that all the variables are independent. Now, in trying to figure out the causal relationship, what we're really trying to do is trying to figure out how probable each one of those four graphs that I've listed. There's more than four graphs. I'm just listing the four graphs. So how probable is the first one? How probable is the second one? How probable is the third one? And so on and so forth. And in figuring out how probable they are, each one of those graphs represents a different joint probability density function across those three variables, the three variables being the child's body mass index, maternal education, and socioeconomic class. So the first one, which you see I've called graph one, conditional on graph one, we can write that joint density function as probability of socioeconomic group times probability of maternal education, and then body mass index depending on both of them. The second one, we start out with socioeconomic group, and then we say that maternal education depends upon socioeconomic group. So you've got that a little probability of maternal education conditional on socioeconomic group. And then the last component of that particular expression, you've got body mass index conditional on maternal education. It's not conditional on socioeconomic group. That's what I mean by conditional independence. If that graph is the correct graph, it says that if I know maternal education, then I don't need to know socioeconomic group to know anything about the child's body mass index. So here are some possible graphs. Our goal is which one is more likely. If we want to actually break the cycle of childhood obesity, we need to try and figure out what way the causal structure is. Now, when we talk about learning a network or learning a structure, the first part, which I've talked about, is the structure of the network. Which one of those four is most probable? And I've written that here as P of the graph, given the data, and that's equal to, this is just a straight application of Bayes' theorem, P of the data given the graph times P of the graph, and there's a bit on the bottom. The bit on the bottom gives us a lot of problems because there's an awful lot of graphs, is just a normalizing constant to make sure that everything, all those probabilities of those graphs add up to 1. But basically you've got, given the data, what's the probability of a graph? That's called a posterior probability, and that's proportional to the likelihood, that's how likely the data are if that particular graph were true, times the prior probability of a graph. Okay, then given a structure, then we need to estimate the parameters which describe that structure, the strength of the relationship, not just whether it exists, but how strong it is and which direction it is, all those sorts of things. Now, it turns out that the first is really, really hard, and we're going to see why, that to figure out the structure of the network. If we know the structure, actually things are not too difficult, but that's mainly because we make very many simplifying assumptions about the distribution of our variables in order to solve problem 1. So problem 2 could be a lot more difficult if we allowed it to be, but we don't allow it to be because we have a lot of, if we did, we could never get past the first one. So there's the probability of the graphs. So now I'd like to do things in threes. I'm going to go through 3 possible why it's so difficult. And if we go back to those 4 those 4 graphs, it turns out that you might think you'd like to determine between 2 and 3, you know, whether socioeconomic group leads to maternal education or the other way around. Well, you can't. Mathematically, those 2 expressions are identical, given any data set. So we have that problem straight away. This is called equivalence classes, and it happens all the time. So, you know, sometimes practitioners go into blind, just using a particular package without realizing that there are these equivalence classes that they cannot determine between. So that's problem one. Problem two is when we learn the structure, the number of possible structures and how difficult it is to learn which of those structures is the true one. So if you take the top table, P represents the number of nodes, M represents the number of possible graphs. So once you get up to 25 possible variables, you've got more graphs than there are atoms in the universe. There is no computer on the planet that can possibly compute all those likelihoods, the probability of the data given those graphs for that many graphs. So you've got to do some approximation to it. And then what's a good approximation? You may say, well, let's just pick off the most probable ones and work with them, and that's a really good idea. But what is most probable becomes really difficult because unlike a normal, it's a max, we're trying to figure out what has the highest posterior probability. If things are really smooth and easy, we can use gradients, and that's very straightforward. That's an easy problem. In this space, the surface that we're trying to search across is all discrete. There are no gradients available. And so we have to come up with clever ways which are still computationally intensive, of trying to make sure that we pick off the highest areas of probability, and that's a really difficult problem. So that's problem two. Problem three is that we've got these mixtures of different types of random variables. Some are continuous random variables, like a child's BMI, that's continuous. Some are discrete, like, for example, the sex of the child, that's a discrete random variable. How do we measure dependency between discrete and continuous random variables is an open problem. And in order to solve the learning of the structure problem, almost all packages use either the assumption that everything is either all continuous or all discrete. Obviously, it's an area of research in the academic community of how we do this better, but that becomes then problem three. So these are the three big problems. And when we look at the problem that we were trying to attack, we had 25 variables, so more possible models than possible networks than there are atoms in the universe. There were a lot of high correlation, means that even over and above equivalence classes, there were many networks that were almost identical in terms of how likely they were. And we had a just mixture of discrete and continuous random variables. So, what could possibly go wrong? We had all these three things that I've just talked about that are wrong. How did we manage them? Now, this slide is going to be technical, so I think I might skip over it a bit. But other than to say, we address the issue of the number of possible structures by using something called partition MCMC. And basically, that is a technique whereby groups of nodes are gathered together depending upon their structure, the hierarchy in the structure of those nodes, and effectively it reduces the number of possible structures. And that's not a bad assumption, but it is an assumption that the graph can be represented in this particular format. So that was assumption one. Using this, we then got the most probable graphs, and we checked for equivalence classes for each one of those probable graphs, and that's a very time-consuming exercise that we did. The third thing that we did was to assume all the variables are continuous, even if we knew they were discrete. So we've done some theoretical work, and where we prove that actually treating everything as continuous is more likely to get better outcomes than treating everything as discrete. So that's a theoretical piece of work that we're just finishing off writing up. So what were the results? So here I'm just going to quickly cut to the chase and about why. I've said now all the problems. What are the benefits of it? You can see we get this picture of what happens with childhood obesity. Now, the childhood obesity, the variable, I don't know if that you can see my mouse cycling around. I hope you can, because otherwise this is going to make it very difficult for you. That is the child's body mass index that it's cycling around there. It's off to the edge, right at the edge. It's surrounded by the parent's body mass index. In the middle of everything is this socioeconomic group, and that's basically driving everything. And this was for 2 to 3 year olds. This is a very simple structure. one of the things, or in fact the only thing that drives socioeconomic status, it was the parental education levels. And so that was a figure that we presented to the Ramsay Foundation. That was for 2 to 3 year olds. If I go now to the various other age groups, we see exactly the same conclusions. We do see the graphs become more complex as the child gets older, because things such as the foods they eat, the amount of activity that the child chooses to do, and in particular for boys, the amount of electronic games that they choose to play become really important. But effectively, all of these things have, all of these graphs have the body mass index on the outside, the socioeconomic status in the centre controlling everything, and the only thing feeding into socioeconomic status is the educational level of the parents. This is a slide that talks about the variability of the particular graphs in cohorts. I'm going to pass through that. What I am going to say is that, when we broke it down by girls and boys, what we found was that there was this strong association with boys and electronic games. So basically, socioeconomic group drove the amount of TV, which drove the electronic games, which in turn drove the activity, and then in turn drove the child's BMI for boys. But this was a pathway that was not present for girls. And so I think that it's important to know that you could get different structures with different subgroups of the data. And that was one of the things that they found very interesting. So when we think about what were the takeaways? So what we set out to do here was to try and learn about the drivers of childhood obesity. And what we saw is really, that it's highly unlikely that any downstream interventions are going to work, because everything is driven by this socioeconomic status, which is in turn driven by the parents' education level. And without a sort of a graphical model to have this causal pathway mapped out, it's really difficult. Everybody knows these things are related, but to see them mapped out like this was very important and shows just how powerful these techniques can be. The Paul Ramsay Foundation, just incidentally, have now changed their focus from studying childhood obesity, and they're now studying social disadvantage, and they're trying to figure out what are the on and off ramps to social disadvantage, and that was a product of this work. So I think that was something that the group took away as a very positive outcome, that we managed to change a large organisation's way of thinking and also their research agenda in going forward. I'm not going to talk about that. I'm not going to talk about, these are things I've been saying throughout. There's 3 pros and 3 cons. What I am going to say as my key takeaway, so what does it take to be an angel? So in all of this, it really is important to define the research question first, rather than to just use graphical models as a way of diving in and doing some data mining. I think that way lies disaster, because you'll end up with a whole bunch of spurious relationships which may or may not be there. The second thing I would say is to work with domain specialists to reduce the model space. By model space, I mean number of available structures. We've seen how many available structures there are. I mean, clearly, working with experts, they can actually say, actually, that class or that node, for example, child's body mass index can never be a parent. I mean, that's an obvious one. So, but that dramatically reduces the search space. And using that information at other points for other random variables, figuring out which type of relationships are more likely or not will also reduce the model space. And so that's why I say it's really important. And the last thing is, it's always important to be Bayesian. And that is because it's the only logical, consistent methodology for really fusing information together. Information from experts or previous research can be incorporated via the prior, information from data can be incorporated by the likelihood. It is, probabilistic graphical networks are probabilistic, therefore to treat them with a probabilistic methodology, I think is really important. And I'm going to stop there and say thank you very much.
Yes, thank you, Professor Cripps. It sounds like graphical models have enormous potential for causal inference and its application to healthcare and beyond. But it also sounds like it's not without difficulties or of scale. So we have time for one question from the audience that we would love to hear your thoughts on. And sure. The question is the issue of scale something that can be solved in the future? What do you think?
So I think so for the issue of scale, I'm going to take it as the number of possible structures, and I think that they can by actually thinking carefully about the research question. What we realize with the Ramsey Foundation, that work, is that many of those variables, like the sex of the child, the age of the child, the parental background of the child, these are not variables that can you can intervene on. So therefore, what we decided to do was to break up the data set into two groups, one of the variables which were modifiable and those which were non-modifiables. We still incorporated the non-modifiable variables, but we had different structures or different causal structures for different combinations of variables which were non-modifiable. So this means that, if you're 16 and you live in rural New South Wales, you may have a very different set of causal factors that lead to obesity than if you live in the centre of Sydney and you're 10 years old with affluent parents. And so knowing that those different causal structures exist for different demography means that you can tailor the treatment depending upon those characteristics. So that's from a practical point of view. From a theoretical point of view, it drastically reduces the amount of the search across the model space, because you've basically removed a lot of variables from the model space and put them into, we have a mixture model where it's a probabilistic mixture model, and that's what we've done. And that's a piece of work that we're currently writing up for publication. Yeah. Thank you.
Thank you very much, Professor, for joining us today.